Hello again. In this final video of vector properties, we're going to try to make some improvements about the kind of inadequate procedure we have for adding two vectors together, such as this. So far we've just been measuring that out really carefully, drawing it really carefully, adopting some scale, and then drawing the resultant vector and measuring that as well. But when you do that, inevitably, your results are going to be a little bit far off just from the human errors of the inability to draw perfectly correctly. So we need to find some way to make things a little bit more accurate, because in physics we don't want to have it just kind of close. We want it as exact as possible. So let's take a look at the two vectors that we can add perfectly together. If I add ones that are like this, one perfectly in the x direction, one perfectly in the y, then we don't need to add them on paper. We can do Pythagoras and get the exact hypotenuse by doing a squared plus b squared equals c squared. And we can do inverse tangent of our y part and our x part to get the angle exactly. So we can get the exact resultant vector in the special case that we're lucky enough to have two vectors that are perpendicular to each other. But what do you do if you have two vectors that are not perpendicular to each other? For example, this one, and well, I guess this is good right now. Those aren't perpendicular. So what to do? Actually, let's make this one something like this. Supposing these are our two vectors. Well, we know we still have to assemble them tip to tail. And if we want to know that exact distance, what we can do is we can take this vector and break him into his x and y components, and do the same thing with this vector and break him into his x and y components, something like that. So here we have an x component of this vector, here's an x component of that vector, and here are the y components of each vector. And we can think of these two vectors as the sum of this plus this plus this plus this. And in practice, it's sensible to combine the two x's together first and then the two y's together second. So we end up with something like this. So let's try this. And you can see that if I offset that a little bit, that the x component of the resultant is equal to exactly the x component of the first plus the x component of the second. That's this one here. And let's offset it a little bit like that. You can see that this guy in the y plus this guy in the y equals that in the y. So you can take two vectors that are at weird angles and turn them into something that's pure x, pure y, pure x, pure y. Add the x's together with the x's, add the y's together with the y's, and lo and behold, you've got a perfect resultant vector who you can get exactly by Pythagoras. You can get the magnitude, and you can get the angle exactly by inverse tangent. Let's take a look at the actual numbers. If I click on this vector, I can see the x part is equal to 11. And if I click on this vector, I can see the x part is equal to 6. 11, 6, 17. Remember that number 17. Let's take a look at the y parts. This guy has a y part of 4. This guy has a y part of 11. 4, 11, 4 and 11 is 15. Let's remember that number. So we had 17 here and 15 here. Let's click on this one. Yep, x was 17, y was 15. If we square those, add them up and take the square root, in other words Pythagoras them, indeed we get 22.7 right there. And then if we do the inverse tangent of the y part, 15, over 17, inverse tan of 15 over 17, put it into your calculator, you'll see you get exactly 41.4 degrees. So here we've added two weird vectors at weird angles, but we got an absolutely exact resultant of 22.7 with an exact angle of 41.4. A fair bit better than trying to add them by measuring and drawing with a ruler and a protractor. Let's take a look at one more example. Supposing you have a vector like this, which is pointing in the positive x and the positive y direction, and you try to add it to a vector like this that's pointing in the positive y but the negative x direction. How would that work with the lesson we just learned? Well, the idea is the same. If we look at this first vector, he's got a positive, let me make sure I clicked on here, a positive 15 in the x direction, and this guy has, let's click on him, has a negative 9. Positive 15, take away 9, that means in total 6, positive 6 in the x direction. Let's take this and throw it over here, and let's take a look at the sum. Is indeed that positive 6? Yep, in the x direction, positive 6. And let's take a look at the y direction. Here we have positive 8. Let's look at this one. Positive 5. 8 and 5 is 13. Let's go back and look at this one. Yep, 13. So we've got 6 in this direction, 13 in that direction. We can Pythagoras those two numbers to get the 14.3 for the resultant. And we can inverse tangent the y and the x. Inverse tangent of 13 divided by 6 should give you that angle right there. So this breaking a vector into components and then adding the components to get the resultant will work regardless of which way your vectors are pointing. And there you have it. Vector addition with accuracy by using components.